So today I want to continue the discussion of condensed abelian groups and in particular I want to start explaining the notion of a solid abelian. So let me recall. So last time we explained the notion of a light condensed abelian group. Well, condensed set, generally condensed abelian group. And so by definition, this was a heap on the site of either of light for finite sets, so pro objects indexed with natural numbers in finite sets, with respect to the topology of certain dimensions. So I want to start with the following theorem, which was from the end of Friday's lecture. So here's the basic results. So okay, so just sort of notation. I think I'm gonna drop the word light forth. So notation, everything will be light explicitly. So we'll drop light. So I'll just write condensed for light condensed. Okay, so here's the basic theorem about the category of light condensed abelian groups. So first of all, condensed abelian groups is a Brownian abelian category. So in other words, presentable and filtered elements are exact. Presentable filtered elements. So it acquires a natural tensor structure. It acquires a natural tensor structure from just from the tensor product of sheets, because it's a category of sheets of abelian groups. It acquires a natural tensor structure. And the tensor structure is continuous in each variable. So it preserves colimits in each variable, and that means that you can talk about internal Homs in condensed abelian groups. So it's continuous in each variable. So internal Homs exist. Internal Homs would be condensed abelian groups. Okay, so again, these two are just sort of general facts because it's sheaves on a site, sheaves of abelian groups on a site. But now I wanted to explain some facts that are a little less formal. One is that countable products in condensed abelian groups are exact. Or equivalently, if you have a sequential limit of surjections, or relatedly, if you have a sequential limit of surjections, it remains a surjection. And sequential limits of surjections are. So part 3 is not true for sheaves in any topos, but as I mentioned last time, it's a key feature of condensed. It's a feature that the site is replete. So this is a consequence of the fact that the site of light for finite sets has countable limits. So you can form a limit along a tower, and a limit of surjections is surjections. So this is because condensed sets is replete. So because you've added these countable limits. So I just wanted to, I mentioned this last time, but I wanted to say one more reason. This leads to the following result, that if you form the derived category of condensed abelian groups, so ultimately a lot of the constructions one wants to do are going to live in the derived category. So the derived category of condensed abelian groups is left complete. So that means in particular that, so this is a useful homological property. It means that it implies that cosmic and powers converge. So so this means that so if you want to work with the derived category, well, sometimes in general, if you're working with the derived category in some of your category, you might run into some issue. You might want to try to make arguments by inducting on the chronological amplitude and so forth, and those can be a little bit problematic if you're not in a setting where every object is a limit of a constant compound. But in fact, that's the case here. It's a consequence of this fact about the repeats. Okay, and then here's the key result. So so key result is that so this particular condensed abelian group. So I'm going to form the free condensed abelian group on the profinite set n union infinity. And the statement is that it's internally compact projective. So in other words, taking the internal Hom out of this object, so take the internal Hom out of this object, it gives you a functor from condensed abelian groups to condensed abelian groups. Roughly speaking, this is sending a condensed abelian group to the condensed abelian group of convergent sequences in it. So this gives you an endofunctor from condensed abelian groups to itself. And so informally, it's sending M to convergent sequences in it. And then the statement is that this functor is exact, so it preserves limits and colimits. So it preserves limits. So we'll say that. So this functor is exact, preserves limits and colimits. And this is also true if you were to replace. So this is also true if you were to replace condensed abelian groups by the derived category, and then to take Arham out of this. This is also true in derived category of. So then the statement is that taking internal Hom out of this object would give you an endofunctor of the derived category, which preserves limits and colimits and is also T exact. So okay, so maybe I just write that over here. Our Hom, internal Hom out of this object, is going to M union infinity length. Condensed abelian groups. So D of condensed abelian groups preserves limits and colimits, and it's T exact. So I think this was one of the key reasons to switch to the life setting. In the non-life setting, when you work with you don't restrict to like profinite sets, then this result is not true, and there aren't enough internally projected objects. Okay. So so this was the theorem, and I wanted to explain. So already sort of explained 1 through 3. I wanted to say something about part 4. But maybe first I wanted to sort of give some examples of what these condensed abelian groups look like, to give some concrete examples, and then in particular say a little bit more about this object here, this free condensed abelian group on a profinite set. Okay, so first I wanted to give some examples of condensed abelian groups. So there was a fact from last time that I at least sort of stated rather briefly. And it states that, so if you have a compact Hausdorff space, then that gives you a condensed set, and that gives you a fully faithful embedding of compact Hausdorff spaces into condensed sets. And those are precisely the quasi-compact and quasi-separated objects. So in general, a quasi-separated condensed set, sorry, I guess I should say light everywhere. This is the same thing as the end category of metrizable compact Hausdorff spaces. So I think I should say that it's not just the end category, but it's the end category where the transition maps are inclusions. So it's the end category, but where you only allow so you can represent a quasi-separated condensed set as a filtered colimit under let me say. So in practice, a lot of the condensed sets and condensed abelian groups that one is interested in arise in the following way. So let's suppose I have a sequence. Suppose I have a sequence of metrizable compact Hausdorff spaces. Metrizable compact Hausdorff spaces. And inclusions. So let's say y1, y2, dot, and inclusions. So inclusions are closed embeddings. So inclusions y1 sitting inside y2, sitting inside y3. So it's an expanding system of compact Hausdorff spaces. So then you can form a new condensed set Y, which is just the column of this diagram in condensed sets. So then you can form.
But I want to say, you do not assume contact it's countable.
I don't.
But there it's just that.
Well, there it's arbitrary because I'm not putting any sort of size bound on the
Okay,
condensed
no,
set.
I just.
Oh, okay, but I think in practice, right? So in practice, the objects that one is interested in, well, a lot of the objects are built from things which are really sort of sequential in systems as well.
And I like that in this case, well, if you have an arbitrary thing, then you cannot represent such a inductive every connection. Not an inductive.
Yes.
Those you can.
You can. So I think one has to be a little bit careful with the products. So I think, yeah, I didn't know this very carefully. So I'm just recalling something I read a while back. So I think it's actually I think it's somehow better to think about the inner system of compact Hausdorff spaces. And because of the issue that if you have a product, so here the example is an expanding system of compact Hausdorff, metrizable compact Hausdorff spaces, then you can form the colomet. So you form the colomet of y sub I in condensed set. So let me just write y sub I underlined to mean the underlying condensed set. Then you can form the colomet as a condensed set, just the colomet of the associated condensed sets. And this is a quasi-separated condensed set. And so these are going to be in practice. A lot of examples are going to be of this form. They're going to be representable. I mean, so equivalently, this condensed set encodes this end system of compact Hausdorff spaces. So I guess the thing to be a little bit careful of is so if you form a product of these, I believe, remember correctly, the product topology is not always the same as the colomet. So the product. Do you think this is I think you're gonna pairwise plot. Well, maybe I should double check this. It's not being recorded. Okay. Okay. So let me give an example. Right. So the example is oh, right, yeah, sorry. So in particular, for a condensed abelian group, we might be in a setting where the y sub i's themselves are not groups. Okay, but there's some sort of multiplication law in the inner system. So, for example, y sub I times y sub j could map into y sub I plus j or something like that. So given sort of compatible multiplications, y sub I times y sub j into, let's say, y sub I plus j. I won't try to write out all that here. Then you can make y is going to become a condensed abelian group. And I think this is kind of how one can describe. So this is kind of how one can describe some condensed abelian groups in practice. They're sort of group objects in sequences, expanding sequences of compact spaces. So just sort of the simplest example of this is if you take the real numbers, then this is the colomet. This is the colomet of the integral from minus n to n as n goes to infinity, and then you have an addition law that well, we'll take the nth integral and map to the n plus n. Okay, so the usual real numbers are expressed in this way, right. So so also we have some other examples. So another example is so the free condensed abelian group on a profinite set, on a light profinite set, can be described in this way. So let S be a light profinite set. So it's a limit, the sequential limit of that. Oh, sorry, let me change S of I for the S of I finite sets. So then you can describe the free the free condensed abelian group on S in such a fashion as a group object in well, so it's quasi-separated, so you can think of it as an in system of compact Hausdorff spaces under closed emergence. So the idea, okay, so can describe C brackets S, again, this is the free object S in this fashion. And right, so the idea is that C brackets S is going to be a union over N of what I'll write as Z brackets S less than or equal to N, where this object of Z brackets S less than or equal to N is going to be a profinite set. It's going to be roughly the objects of L1 norm at most N. So this is going to be the inverse limit over I of Z brackets S of I, but then you take those objects whose L1 norm is at most N. So in the free abelian group on S of I, you can look at those elements such that, well, the sum of their L1 norm is at most N, and that's a finite set, and that's compatible with the condensed graphs. And then you can form the limit of those, and well, that's going to be this bracket S less than or equal to N. That's a profinite set. And now you can define a group law. You define the group law on a bracket S is such that well, yeah.
Oh, I'm a bit confused. So what is the L1 norm?
The L1 norm means small L1, the sum of the absolute values of the coordinates. So you can write every element here as a linear combination of the elements of S of I. I'm taking the sum of the absolute values.
Oh.
Yes.
What is
I believe so. So I think the idea is that okay. So let me just right. So Z brackets S less than or equal to N. It receives a map from okay. So let's say -1, 0, 1 to the N, cos S to the N, which is again. So if S is finite, this is well, you just take N elements of S and well, multiply them by these signs and add them together into here. And this is surjective for a finite set. And when you pass the limit, this is surjective for any profinite S.
yes?
Yeah, and you can do this for a compact Hausdorff space as well. Yes. Right. So okay. So the idea is that this. So right. So this is expressing this profinite set as a quotient of a profinite set that we get from S to the n's. Well, a finite copy of S to the n's. So maybe a simpler example. Maybe I should have said so. Simpler example is instead of taking the free abelian group on S, we could take the free commutative monoid, and then it would be kind of similar, but instead we would be forming the nth symmetric power of S. So to form free, let's say condensed abelian monoid on S, then you would take the symmetric powers, sim n of S, so S cos n, and then you quotient by the sigma n action. And then the free abelian monoid would be the disjoint union equal to 0 of sim n. So it's a countable coproduct. So in this case, it's literally a countable coproduct of profinite sets. Okay, so this is an example because z brackets S is an increasing union of these profinite subsets z brackets S where the L1 norm is utmost n. And then when you add the things of less than or equal to n to something of less than or equal to n prime, you get something less than or equal to n plus n. So, okay, so I wanted to do an example of this that was a little bit concrete, which is the case, well, the case that's actually particularly relevant to this business. So let me assume S is a profinite set n union infinity. And let's describe, well, let's say not z brackets S, but actually z brackets S mod the point at infinity. So let's describe z brackets, right, so z brackets n union infinity mod z. So again, this is roughly the object that co-represents null sequences in a condensed abelian. Okay, so an observation. Right, so an observation is that this is actually a commutative ring in condensed abelian groups. So this object, this is a condensed commutative ring. Right, and so that's because okay, so when I say n, I'm including 0 in it. This is a condensed commutative ring, and that's because this n union infinity is a commutative monoid. N union infinity is a commutative monoid under addition, and infinity is somehow an ideal in that commutative monoid. So because n union infinity plus is a commutative monoid, and infinity is an ideal. So you're supposed to think of this object. So this is a condensed commutative ring. We're here. You're supposed to think of this. Okay, so I'll write. So denote. So again, I guess I'm using the notation for Nelson and Tulsa. I'll write this as z brackets q. Put a hat on it for this ring. The idea is that this is something, so Q here is a class of 1 in this group ring. The idea is that this is in fact very much like a polynomial ring. Its underlying ring is just a polynomial ring. So the underlying ring is a polynomial ring z brackets q, but the condensed structure is somehow remembering that the powers of q should be going to 0. Because of this sort of profinite structure, the idea is that the powers of q here are going to q to the infinity, which you've modded out by. But q is somehow topologically nil. That's sort of the intuition behind, that's sort of the intuition behind this condensed ring. So I guess it makes sense as written. Yeah.
Is this more than what we, just more than how is it related with formals? Because naively you could consider formal series.
Yes.
How is this construction related?
So this is actually going to be, well, modulo this topology. This is basically a topology on just the polynomial ring itself. This is not smaller. This is not the power series.
It's a smaller thing.
So let me explain what it is of the condensed ring.
So this is yes, so that's
Not quite the QAddict one. It's going to be, yeah, so let me say a little bit more. So, so what is a condensed structure? The condensed structure is that it's as follows. So the condensed structure is that z bracket, well, first of all, z brackets q, it's going to be the union of the polynomials that again have L1 norm at most n. So it's the union over n of z brackets q, where the L1 norm is at most n. Okay, the idea is that on each of these stages, so here you have a polynomial whose the sum of the absolute values of the coefficients is at most n, and over here we're going to in fact give it the q-adic topology. So z brackets q less than or equal to n. Right. So here, z brackets q L1 less than or equal to n. So this is going to be a profinite set, and it's going to fit inside, let's say, well, if the total L1 norm is at most n, then all the coefficients are at most n. So it's going to sit inside a countable product over the natural numbers of minus n to the n, minus n, n, and it's given the subspace topology. So let me just say concretely what this means in practice. So for each n, if you restrict to polynomials of L1 norm at most n, then in fact the topology or condensed structure is given by a metric, and you can define it via some sort of, if you like the some sort of q-adic. It's not quite the q-adic. It's going to be. I mean, it's going to be the
Yes. So when you write L1,
yes.
but you go, so you put it all down, so say around the way. So
Yeah. So explicitly, right? So for example, we have that the sequence 1 q squared and so forth converges to 0 in this topology. But the sequence 1 2q 3q squared 4q cubed, the dot does not converge to 0 because it doesn't sort of remain in any of these given profinite sets. So it doesn't stay within a profinite set. So if you want to say when a sequence of polynomials converges to another polynomial, the answer is, well, first of all, they do have to converge in the q-adic topology, but in addition, you need a uniform bound on the L1 norm on all of the polynomials in question.
so maybe this has something to do with the architects.
So it also, right? So,
What is the purpose of this?
So in the solid theory, this ring is in fact going to be replaced by the power series ring. But so Klausen and Schulze have also shown that there are other completions of this ring, well, that see some Archimedean phenomena. I guess we're
Yes. So this is what I expect. Because,
yes. But even if you want to construct the solid theory, you still have to contemplate something like this. Was there another question? All right. So okay, sorry. So right. So let me just say okay, yeah. So if you like, right. So I'll just repeat again. So for each of these, if you have a sequence of polynomials, so f1, f2, f converge to g if they do q-adically. So that means the coefficient of q to the I eventually stabilizes. The coefficient of each power of q in the sequence of polynomials f sub I eventually agrees with the coefficient of q. But also there's a global L1 norm. So L1 norms are uniform. Okay. Yeah, so I think in the lectures, they study, variants of this ring, sort of completions of this ring, where you do allow certain power series, but you have some sort of growth condition on about the coefficient. So these are some intermediates between, yeah, you can do this out in theory or like more down in the stuff theory. Okay. So, okay, so, but anyway, so that's sort of the key. All right, so, let's see. So what I want to do now is, I want to explain I want to say something about the proof of this fact about n being infinity. So so let me start erasing on. Oh. Okay, so let me remind the theorem. So the theorem is that as a condensed abelian group, this object, well, z adjoint n union infinity, or equivalently, we could say z adjoint q hat, is internally projected. So theorem 4, z hat z adjoint q in condensed abelian groups is internally projected. So I will prove a weaker form of the statement, and I will prove proof of part of it. So the key result is that if you have a surjection of condensed abelian groups, and well, if you have a section of the target over n union infinity, then you can lift that to a section of the source over n union infinity.
So
Is internally projected. So I will just prove that it's projected. I will prove that follows it.
the way to describe the internal form. Why? What is what?
Well, again, I guess the intuition would be that the internal hum is some sort of function space of hum results.
Yes, let's suppose that
Yes.
what is,
So there's a tensor product on condensed abelian groups because condensed abelian groups are sheaves on site. And so it's the internal hum with respect to that tensor product.
yes. There direct way to say so. First of all, so what is the internal form? Category sheets of data sections of some. This is automatic base. So, no, the group of all citizens from this. So, is there a way to continue this type?
I mean, right. So just
Because my understanding is.
Yeah. I mean, I was only gonna say this sort of thing that you have to think that the internal fluid F and G are condensed fluids. Then you have internal Homs from the P as the G as condensed fluid. And this is explicitly it sends a profinite set S to just ordinary Homs from F tensor Z brackets S into T. Yeah.
So the possible stack of like function that's really that like product.
Yeah, so maybe it's worth right. So thanks for right. So in the non-light condensed theory, there are enough compact projective objects, which are these extremely disconnected sets, profinite sets. However, so there are very few, or possibly even no. Well, there are very few. There are not enough internally projective objects because the tensor product of these projective objects, these extremely free objects on extremely disconnected spaces, is no longer of that form. So the product of extremely disconnected spaces is not extremely disconnected. So in the light setting, you don't have enough projective objects anymore because these light profinite sets are not extremely disconnected. However, you do have this one particularly important object, which is not only projective but internally. Maybe I should also just say that there's a discussion of this in, I believe it's the appendix to lecture 3 of the complex geometry that's found in complex geometry lectures. Yes.
The product here is also the objection over some.
Yes.
F is yes, that's a product of the essence. So for essence, it's equal to S times T.
Yes.
Well, but very complex stuff. Yeah. That's how I just show that it's not find it. So is it a Schultz's?
Yes. So there's some lecture notes for a course taught by Austin and Schultz. Actually, a couple of years back, but they discuss a lot of these.
And on the web page, it's about as a course or stuff.
Okay, so the title is Condensed Math and Complex Geometry. So they discuss some of these issues. So I should also say that these are really issues that are that are more serious in the Archimedean setting, because when you do actually solidify, so it's not in all condensed abelian groups, but when you move to solid abelian groups, then you have compact projectives and internal projectives. So you have everything that you want. But to actually get there, you have to still start somewhere. And okay. So this is actually right. So this is somewhat surprising because well, either Z brackets Q or equivalently Z brackets N union infinity. And this is somewhat surprising because N union infinity is not an extremely disconnected profinite set. And right. So this is really saying, and this is really a property of light condensed abelian groups and not for light condensed sets. So okay, so let me, yes.
I have a question. What's the relation between of Z brackets S and G?
Yes. So if you were to just say Hom, they would be the same thing.
Okay.
But the internal Hom is remembering not just sections of G over S, but sections of G over S cross T for any light profinite set.
I see. So in the setting that balance asked where F is Z brackets.
Yes.
Then this internal Homs are
So it's the condensed abelian group that's sending G to sections of G over S. Sorry, that's sending a profinite set S to second.
Right. You're explaining something basic things which for us.
transform Z brackets T into G is the condensed abelian group. Which sends S, which is a light for a finite set, to sections of G over S cross T.
Is it an internal?
Oh, thank you. Yes, that's the meaning. Okay, so this is if T is a light for a finite set.
And we are particularly interested in this where T is the positive integer.
Yes.
I would call this M bar. So
So I will explain a proof that it's projected, and the fact that it's internally projected is also there's an elaboration of this. And so we'll show that the functor that carries a condensed abelian group F to sections of F over n union infinity is exact.
suppose the internal projectivity right?
If the unit is projected, which it is in condensed abelian groups.
Why does it?
So the unit is projective in condensed abelian groups because any cover of a point splits. So so the unit is internally projective. So if something's internally projective, then it's also projective. Okay, so I will just sketch the proof that that it's projective, and another way of saying it's projective is that if you consider the functor that sends a condensed abelian group to its sections over n union infinity, then that's an exact functor in F. So okay. So in fact, to see this, it's enough to show that H1, so this is a site, so we can talk about cheap homology, that H1 always vanishes. So it's enough to show for any G in condensed abelian groups, H1 of G, sorry, I guess I should write H1 of, well, I should write the input first, write N bar, which coefficients of G is equal to 0. So this is enough. Okay, so how do we do this? Well, we know that right. So suppose have a class which we'll call alpha in H1 of n bar with coefficients in G. So whenever you have a class in H1, you can annihilate it upon some cover. So there exists a light for a finite set T. So light for a finite set T with a surjection from T to n bar, such that alpha, when you restrict it to T, is equal to 0. So by definition. So now the idea is that we're going to replace T. So the problem is that this surjection doesn't have to have a section. So n bar is not extremely disconnected, so this surjection might not have a section. But what you can always do, yes, so T is compact metrizable. Yes.
So what's the problem? So you can bar you have 0, 1, and so for that research. Why? Because you can yes, you get a sequence and it has a
Subsequence, but not. Yes.
So you can find, right, so over the natural numbers, you have a sequence. And you can lift that to a sequence upstairs, but it doesn't have to converge upstairs. It could have many different limits. So that's a problem. So you don't necessarily have a section, but you can do exactly that. So pick a section of not the map from T to n bar, but the restriction to just the natural numbers. So T to n restricted to the pre-image of n. So let's say x naught f to n. So that just means you pick a sequence in T. And well, the problem is it doesn't give you a section of the map f because the sequence of T doesn't have to have a limit. It could have a whole bunch of points. But what you can now do is okay, so you can take the closure. So you can take the closure of that sequence. So i.e. this is the sequence in T. And it's projecting to 0, 1, 2. And now, well, you can take the closure. So take the closure of this section. So take the closure in T of this sequence or of this section. So now this is going to give you a subset, a closed subset prime of T, which it's going to map by an isomorphism to the finite part of n bar. So it's going to map by an isomorphism when you restrict to n, but it will have sort of potentially a lot of stuff at infinity. So okay, so let me get here. So this gives closed subset prime sitting inside T, such that prime is still going to map surjectively onto n bar, and it's going to be an isomorphism away from infinity. So let's call this f prime away from infinity. I.e. f prime inverse of n perfectly. So it's kind of, so you can think of T prime as some sort of compactification of the natural numbers. It's not just a one-point compactification because there are many different ones. So let D prime sitting inside T prime be the pre-image of infinity. So these are all the limit points. All the limit points upstairs. And then the idea is that so this is so T prime is sort of so T prime maps to n bar. It's isomorphism above n, but it possibly has a bunch of extra stuff at infinity, which is this T prime. So you get a push-out diagram in for fun and sense. So, well, it's a little, I don't know, it's a little bit like a blow-up. So you have D prime is a closed subset of T prime. T prime maps to n bar, and here you have just the point at infinity inside n bar, and this diagram is a push-out. So this map is an isomorphism away from this. A little like a blow-up. And this is going to give you a Mayer-Vitor sequence in cohomology, in condensed cohomology. So you get it from this, you get a sort of Mayer-Vitor sequence. In T cohomology. Okay, so right, how does this go? So you have well, so first of all, you have H1 over n bar of f. And you have your class alpha in here. And then this is going to map to H1, it's going to pull back to H1 of these two things. It's gonna map to H1. So I'm gonna drop F, it's called the F. So it's gonna map to H1 of T prime, direct sum H1 of this point at infinity. And by construction, alpha pulls back to 0 on T. So it also pulls back to 0 on T prime, which is a subset of T. And then it pulls back to infinity, which is just. So alpha maps to 0 via this map, and that means it comes from the connecting homomorphism. So the connecting homomorphism is going to go from H0 of D in here. So alpha must be, so since alpha maps to 0 over here, alpha must be hit by some, I don't know, alpha tilde in here. Okay. Sorry, that's a D, I wrote D, but I guess I should really. And now we can also continue this because, right, so if we continue this, if we continue this, we would be getting H0 of prime direct sum H0 of infinity mapping to H0. So what it's just the long exact sequence, along the Mirabay-Torres sequence. So you can write out the Mirabay-Torres sequence with this decomposition. So what we're interested in is an H1 of n bar. We have a cohomology class that restricts to 0 on each of these loci. So it's in the image of the boundary map. So it's coming from this is beautiful. It's coming from the boundary map from sections over D prime. But now what we also know is that if we continue, the Mirabay-Torres sequence continues, and the boundary map from H0 of T prime into here, it annihilates anything that comes from H0 of T. So, okay. So now actually we're almost done. And the point is going to be that this map is actually surjective. So the key point is that this map actually is automatically surjective, which is going to tell you that this map is 0. And that means that alpha is 0. So the key point is, okay, so key point is that the map, the restriction map from H0 of, I call it H0 of T prime to H0 of D prime is surjective. And that means just by chasing, well, looking at this exact sequence, this completes the proof. Because this tells you that alpha tilde equals 0. Well, I'm sorry, it tells you that alpha tilde is in the image of this map. That alpha tilde is in the image of this restriction map, and that implies that alpha equals an exact sequence. So in fact, this is just a general fact in light for finite sets, and is another sort of key observation. Whenever you have a closed embedding of light for whenever you have an inclusion of light for finite sets, then you can always extend sections with any sheet. And the reason is that, so in fact, in F, yeah, so I stopped writing F because I ran out of space. Oh, that is a good point. Yes, F sometimes became F. All right. Well, I guess I didn't write F too much. But yes, all the sections are of D. All right. So here's the so in fact, if you have a section of any sheet, this is somehow generally over a closed subspace, you can always extend it to a larger space in this context of light for finite sets, and it's based on the following lemma. Any inclusion of light for finite sets has a splitting. Right, so any inclusion, let's say y1, y2, in light for finite sets, and actually here I believe lightness is important, has a section. Retraction, yes. Has a retraction. And in particular, this means that for all, let's say, G in condensed abelian groups, if you have a section of G, so just a point from Y1 into G, so section over Y1, then you can extend it to y2. So the map from g of y2 to g of y1 is certain. Just because you can precompose with this recursion. So this is a lemma, and since I'm a little bit behind, I will just say that it's not too hard to prove. Well, in fact, it's not too hard to prove by thinking about countable inverse lemmas. And in fact, there's a statement that like profinite sets are injective in the category of profinite sets. So this is, I'll just say this is a sort of elementary argument with countable inverse. Well, let's say sequential improvements. Well, I mean, any inclusion is automatically a closed. These are compact cases. Any continuous. So that is the proof of this fact. So yeah.
So is it true classically that if we have sheet on like profinite set, then it's automatically solved?
I mean, I guess this is kind of saying that, yeah. Okay. Well, sorry, it's not a sheaf on an individual like profinite set, but on all like profinite sets. It's saying that you have a function.
Oh.
Yes, all higher chronologies also. Sorry, I just wrote it for a good one. Oh, no, that is specific to n bar. So right, so the question, right, okay, so the question is, does the cohomology, so in particular, right, so we showed that I said H1, but well, this applies to all the HIs then. The cohomology of any condensed group over n bar is 0. But that I think is really specific to n bar, and I will again refer to this condensed this complex geometry document. There's a discussion, and they show that in fact this is not true. It's related to some, I think, some sort of, well, actually pre-existing problems in Banach space theory. It's not true over more general profinite sets. So it is really something specific to n1. Yes. So they appear in, if you want to, so okay, so the claim is that there are examples of G such that there are cohomology classes over other profinite sets, and they come from Banach spaces. So I guess it's, yes.
But here, it does not because the topology it's not a topology. We can see that, but this topology of subjects.
Right, sorry. So it's not the cohomology on the individual space as a sheaf on the individual space. It's a cohomology on the site where you allow all dimensions, not necessarily just like stuff that space. So okay, so since about time for a break, I'm going to, I think we should pause now, and then so after in the second half I will explain the notion of a solid R module, and yes. Okay, so in the second half of the lecture, I will discuss the notion of a solid module. So okay, so let's say R is a commutative ring. Possible ring. And following definition. So definition, so a condensed R module. So just an R module.
First lecture, there was a certain non-competitive.
Yes.
Right. Which was more or less a ring of certain hypothesis.
Yes.
And this is a
Oh, sorry, this is any
This is
commuter,
the
but no relation. Sorry. We'll come back to it. Yeah. Okay, so a condensed R module. So let's say we have just a commutative ring and a condensed R module. So an R module in condensed, like condensed abelian groups. And we'll say that it's solid if it has the following property. So it's R solid. Well, I should really say R solid. So here is R solid. If it has the following property. So okay, so for all elements R, so let's recall that sorry, I should give this module a name, so let's call this N. Let's recall that we have the object of null sequences in N, so recall that this is so the condensed abelian group, or in this case R module of null sequences in N. It's the internal hum from Z brackets Q count into so this is the condensed abelian group, or in this case R module, because M starts life as an R module. It's the module of all null sequences, sort of parametrizing null sequences. And then there's the following condition. So for every element R of the ring, I'm going to consider the following endomorphism of null sequences. So the collection of null sequences has an operator called the shift operator. That just comes from, well, on the profinite set n bar, you can shift by 1. And the condition is that the map, so let me write it this way. So for all R in R, the map 1 minus R times the shift operator. Sorry. For space. So 1 minus the element R times the shift operator from null sequences of M to null sequences of M reduces the positions. So the idea is that if you have a null sequence, so roughly speaking, heuristic, what is a null sequence? So if M0, M1, the dot is a null sequence, then you're supposed to be able to, form. So how would you invert 1 minus R times the shift operator on a null sequence? You would you would do something like this. You would form right. So in particular, the starting term would be I guess it's M0 plus R times M1 plus R squared times M2 plus dot. Then I guess the next term is going to be M1 plus R times M2 plus R squared times M3 dot, and so on and so forth. So you're supposed to be able to form. So the fact that 1 minus R times the shift operator is invertible is supposed to be saying that you can perform certain sort of infinitary operations on a null sequence. So maybe I should have just assumed R equals 1 for simplicity. So let me just say R is equal to 1. So say R equals 1. So then if you have a null sequence, you can form so then you can form the way that you would invert 1 minus the shift operator is that you could form sum from mi from I equals 0 to infinity, sum of m sub I from I equals 1 to infinity, sums from mi from I equals 2 to infinity, and so on and so forth. So this is exactly what you would expect to be able to do in something like a complete non-Archimedean topology. So you would expect and do this in a complete non-Archimedean topology, and that's in fact what solidity is supposed to capture. Now we said not just solid as an abelian group, but solid as an R module, and roughly speaking, that's saying that you're also allowed to put in R's in these infinite sums, which I mean I think it's sort of saying that the topology has some sort of weak R linearity. So, well, so so you should maybe rough heuristic, again, rough heuristic is to think about topological R modules, say complete topological R modules. Topological R modules with a basis at 0 of R modules. And I think this is a good heuristic, at least if R over Z is a finitely generated ring. So if you have a finitely generated ring, then the condition of being solid as an R module, it's supposed to capture a topological R module, but where the topology is given by some sort of neighborhood, you have a neighborhood basis at 0, which is itself given by R modules, and it's complete for this. Yeah, so we can start by thinking R equals Z, but eventually we'll want this reduction. So I think this is at least sort of formally a little bit analogous to the notion of derived completeness. So okay, so right. So again, this is supposed to be like a completeness, some sort of completeness condition on a condensed R module, and maybe some analogy is that so analogy. Okay, so let's say n is an abelian group, classical abelian group. Then we'll say that n is derived P complete. It has the following property. P is a prime number. Or, well, I mean, yeah. Doesn't actually. I mean, P could be just any element of a ring. So we'll say that it's derived P complete if, okay, so let's look at, instead of looking at this, the null sequences in M, let's look at sequences in M. So let's say sequences in M is just Cartesian product over the non-converse in M. There's all sequences in M. And the condition is that, okay, so the condition is that 1 minus P times the shift operator on sequences in M, the sequences in M. Right, so that should be nice and works. So, so this at least has some sort of formal resemblance to the notion of solidity, except that except that here it's a statement on sequences rather than null sequences. So I think this is a very rough analogy, not really such an accurate analogy, but I just wanted to point this out because one of the motivations for introducing the notion of derived P-completeness is that, well, there's a notion of an abelian group being classically P-complete. In other words, M is the inverse limit of n mod P to the n times n. But one problem with that definition is that the collection of all classically P-complete abelian groups does not form an abelian category, because that condition doesn't really behave well with the exact sequences. But if you look at this condition, it clearly is going to give you an abelian category, because the construction of the sequence space of M is exact. This is an abelian category for those generates abelians. The abelian category goes through extensions. And that's just because, so just because M goes to sequences of M is an example. Okay, so let me just make a couple of remarks. So another remark is that okay, so if M is okay, so again it's a condensed R module. N is solid. If and only if. So again, this is going to be sort of unwinding, but if and only if for all sort of condensed abelian groups equipped with a topologically nilpotent endomorphism, which is to say all, let's say, Z brackets Q modules. Well, maybe just for simplicity, let's say we're over R. So all R brackets Q at modules N hat, so remember Q hat, the powers of Q hat convert to 0, so Q hat is somehow topologically nilpotent. Then we can form the internal Hom over R from N to M. And now that has an action of Q hat on it as well. And the statement is that, so I guess 1 minus R times Q hat acts as an isomorphism. ISO for all R. So I guess it's equivalent to saying, it's also equivalent to saying, because these are internal Homs, it's just equivalent to saying that internal Hom from R brackets Q hat mod 1 minus R times Q hat into M is 0. Okay, so this is, maybe I should have said this first. So this is another, so this is, sorry, I should have said, maybe this is sort of actually the key point. Should have said a little bit more. So to say that N is solid, it's the same thing as saying that if you take internal Hom from R brackets Q hat mod 1 minus R times Q hat, the internal Hom from there into M is equal to 0. And that's for every element R of the ring. So the condition on an R module being solid is just saying that some internal Homs from these objects into it are 0. Okay, so well, I think it's basically because
it seems that the picture that of a quotient,
yes.
still means that something is in chair.
Oh, should I say?
Because
Oh, I'm sorry. You're saying I should have said R Hom. That is a good point. Yes. Thank you. Thank you very much. So I should say X is 0. That the X group is vanished. Okay, thanks a lot. Maybe I should write that actually. I should write that more carefully. So let me actually continue over here. Actually, that segues very well into what I'm going to say next. So, okay, so definition.
sorry,
Yes.
that also should I able to extend that almost.
It's going to be. Well, yeah. So again, if R is like finitely generated, it's going to be that. But that's a theorem one has to prove. So yeah, I wanted to say something about that. Okay, so let me use the following. So let me just write G of R to be the derived category of condensed R modules. So just instead of writing D of condensed R, I'll just write D of R to mean derived category of R modules of condensed abelian groups. Yeah.
Sorry, so the R of Q hat refers to the ring R of N.
Yes.
So what is multiplication by Q hat?
So I mean I can form multiplication by Q hat as an endomorphism of that as a module. So Q hat is an element of the underlying condensed underlying ring. So it's going to act on it by multiplication. So like Z brackets Q hat has an endomorphism of multiplication by Q hat, which is just another name for this strict operator. Okay, so we'll say that M and T of R is solid if okay, so I guess I can say it that way. So if R Hom, well, either R Hom from R brackets Q hat mod 1 minus R into M equals 0, or R and R, or yes,
and you have to take as R tensor as Q hat.
yes, R brackets Q hat is R tensor over Z with Z brackets Q hat, and this here was Z adjoint N bar mod infinity. So, or equivalently, if 1 minus R times the fifth operator, right? So again, you can form null sequences on M in this derived context as well, because again, it's some internal Hom, and this should give you an automorphism. Sorry, sometimes it's convenient to use this description as well. And yeah, so this is okay. So if you say it this way, it's really in the derived category.
Oh, but it's like the way are.
Yes.
So the model is after all the same as the right model. So
Yes.
Is there similar description for more general rings? Suppose you have a arbitrary or financial
Yes.
Is it after all true that so that model that's model for
For a finally generated.
for finite yes, okay, so if R is then all this is eventually is not weakness.
That's right.
Maybe you can make it a simple style. The best one, yes, is really short.
Yes. And so yes.
And for for not for individual things for some reasons this yes, but can still define. So my dream is to eliminate what which finance sense and so on. I understand what this is vulgar. I'm trying to so much part of ethics. Also, which is not very like but maybe it was their efforts language like the finance sense it's so the liquid version maybe it's not so simple so
I agree. It's not strictly necessary to define the solid.
okay. So it's not strictly so the good news that you confirm that all this business all this sophisticated business not necessarily from the solid. Yes, most relevant for us for the needs. Yes. This is so, but maybe you will. So, as you said, this description there also this is correct for financial generator. But not for general. So maybe for general events there is some modification. Yes.
I mean, I think you can describe it as a filtered column in categories. So and
so in other words, you have adaptives. But if you have an infinite generated derivative with R, then that will for any finite generated subplane R will consider corresponding with indices. Models and then take the coordinate. Yes. Like sense, but just well, like a few and so convergence. And define them just as it's a true event. If you just try to define well a version of condensed models over this very poor categories, and the result would be the category of solid numbers. That's very weak.
Sometimes, we discussed this briefly in the course. So yeah, so the question was, instead of considering all like finite sets, what about finite unions of n bar? And I believe also this was a version that was considered before. I think there are let's see, so I think one motivation for them is probably that they want to consider things like, let's say already want to consider something like the Z2, like the p-adic numbers. And that's us.
Yeah.
Well, I think so. Okay, so I think I'm not sure I have an answer to the question of like, would you get the same if you started with that category and tried to do some of the localizations? Where would you start to get different answers?
But wouldn't it be exactly for public classes that the models versus expansion is not exactly.
Well, I think you would still need, so you would still need to add some completeness. Now, like if you take sheaves on n, just on n, like so the maps. I mean, yeah. So there are certain. So the thing is, there's going to be a solid completion as well that appears. So if you take maps from Z brackets, you have to. Well, they're not. I think there are not enough endomorphisms of Z brackets. I think. Well, yes. So for example, you would like you would like to be able to form a lot of infinite sums. You would like to be able to define an endomorphism of Z brackets U hat, which is like multiplying by some power series whose coefficients are unbounded. But I think that is not continuous as an endomorphism of Z brackets U hat. I think the answer is that you would at least need to do some further completion in any case.
So that people yes, science same as
yeah, so I think I don't know the answer to that right now, but I think I just was clear that we would have to do some completion. We probably have to make a similar definition in that context. Okay, so so let me write. Okay, so write E of R solid. Solid E of R for the solid objects. And so now let me state the following theorem. So the theorem is that theorem one is that if R is solid. Well, let me see. So R itself belongs to D of R solid. Two is the D of R solid, and also just so just the category of solid molecules. In solid molecules, solid R molecules are stable under limits, colimits, extensions. And internal hum R out of any object. So any x, not necessarily solid, any x in V bar. Sorry, and here I'm saying I consider D of R solid as a subcategory of D of R. So if we look at the solid R mod, the solid objects as a subcategory of D of all condensed R modules, that subcategory is stable under limits, colimits, extensions, and archons added in. Okay, so 3 is that an object M in D of R. Yes.
But when you say something are modules, not derived,
Non-derived.
but are that of the that they are
Okay, so then I guess instead of archon, I should say internal texts. Yes. Archon or internal text. So I guess I'm taking the result both for the derived and the non-derived version. And then the last part is that an object in D of R belongs to D of R solid, so it's solid as an object in the direct category, if and only if all the cohomologies, each of the individual cohomologies is so I of M is solid as an So an object is solid in this derived sense if and only if each of the cohomology terms, which are just classical R modules, classical condensed R modules, are their solid instances. So solidity is something that you can track on a level of cohomology. So this is a theorem. And right, so the point is the theorem actually, there's actually not too much one has to do to prove it. The point is that the definition of solidity is in terms of maps out of internally projective objects, out of internally compact projective objects, and so this actually follows sort of directly. So it follows. This actually follows directly from M mapping to null sequences in M, preserving limits and colimits, and also being key. That's what compact projectivity of Z brackets we have is sort of finding. So the point is that this condition of being solid, that it's this is a condition that sort of passes through to homology, it can be used with limits and colimits. So that's sort of the very nice thing that happens in this. So the next thing to say is that there's a tensor product. So this is actually a formal consequence of the theorem as written. So let me just say a couple of consequences. Yes, corollary consequences. So one is that the inclusion of D of R solid inside D of R admits a left adjoint. Called solidification. Have an arbitrary R module, or arbitrary object of D of R, is a universal way of solidifying, forming a universal object of D of R solid when it comes to. So I'll write that as N mapping and solid.
and so the diffusion in kind of modern version of the notion of completion.
Yes.
Solid perfect response.
Yes. And then also D of R solid acquires a symmetric monoidal structure such that solidification, which is a localization, is symmetric monoidal. So acquires a canonical symmetric monoidal structure such that M maps to M solid is symmetric monoidal. So this is something general. I mean, it's basically that this is a localization. This is a Bausfield localization construction, and it's a Bausfield localization that at a class of morphisms basically at a tensor ideal. So it's a Bausfield localization that's annihilating a tensor ideal, And so that's why, so general theory is telling you that that is going to have a symmetric. So there's a solidified, so this is actually one of the key points, but there's a tensor product on solid harmonic, solid tensor. So we want this. So we want a solid tensor product because we would like the tensor product, the completed tensor product of, say, z double brackets t with z double brackets u to be, so example, so we're going to show this later. Right, so v double brackets t tensor over v solid with z double brackets u is going to be z double brackets t comma u. Now, this would not be true just in condensed abelian groups, because when you form the tensor product of condensed abelian groups, it just does their neutral tensor product, ordinary tensor product, on underlying abelian groups. So this statement is only true after solidification, and is one of, I think, the motivations for having a solid tensor product that you want, well, otherwise you can take the tensor product and uncomplete things there won't be, complete things there won't be. Okay. So this is a theorem, and okay, so this is a theorem that's essentially already a consequence of what's done, and this is sort of the general code. Yes, because R itself is solid.
So that there this object hardware sound that
Oh, G of R solid. So R solid, G of R solid is as a category. So R solid is the same ring, but it refers to a different the category of. So D of R solid, the notation is that D of solid refers to the solid harmonics. So actually, maybe I should sort of point this out. I mean, this is just, I mean, this is terminology that's somehow essential to what they're doing. So they define, I mean, essentially they axiomatize this sort of list of properties is what they call an analytic ring. So, like that. So definition, an analytic ring A consists of, well, first of all, an underlying ring. So I'll write as a triangle, which is a condensed ring, a light condensed ring. And actually, more generally, it will be allowed to be an animated ring. Okay, so that's part one. And then part two is a subcategory of complete modules. So we can form G of a circ. So a subcategory, well, okay, so first is you can form G of a circ, which is going to be the derived category of a circ modules and condensed abelian groups. And one is required to give a subcategory G of A sitting inside G of a circ of sort of complete objects, which basically satisfies all of the above. Satisfying the above conditions. So for example, it's closed under limits and colimits. Limits, colimits, and internal columns. And it's stable under, okay, and it's detected on at the level of cohomology groups. So an object of D of A circ belongs to D of A if and only if the cohomology groups, well, considered as elements of the heart, belong to D of A. Maybe I should just write this. So M in D of A circ is in D of A if and only if each homology module in child M belongs to D of A. Okay, so this is what they call an analytic ring. And I left off one important condition, which is that A itself belongs to D of A. So A circ. A circ belongs to D of A. So a circ is it's an object here, and it needs to be complete. So this point is. So this is called an analytic ring. So it's not only a condensed ring, but it's also the solution of a complete module. And then again, sort of by general theory, D of A, quad D of A sitting inside D of A circ has a lot of joint, so completion to joint, and a canonical symmetric nodal structure such that completion is symmetric nodal, so the same as nodal structure such that D of A circ to D of A is symmetric. Okay, so again, the symmetrical nodal structure is that if you have two objects of D of A, you just form the tensor product over A circ, and then you complete it again. So that's how you form the solid tensor product. You just form the tensor product of condensed stabili groups, and then you solidify it again. Okay. So I think one of the one of the insights of Clausen and Schulze is that one of their suggesting is to use these as sort of instead of using ordinary rings or animated rings, to use analytic rings as sort of the building blocks for their
Probably this is a great issue, but well, let's try to develop what is so that question. One is the classical problem. So we saw that the notion of solid group is a modern version of logical. So is there kind of classical prototype of this? So there's another question.
Yeah.
Let's try a very right of the define basically one could think of this why don't we choose functions? Well, solid groups with a ring structure. And all solid different groups form a tensor function. Yes. Then consider objects inside this approach. But this is not what the
Yes.
So what would be wrong? This guy.
So I think I would say a couple things. So one is that I think what they're saying is that one should, instead of considering ring objects in a tensor category, one should consider sort of, so maybe I should write something. Part of what they're saying is that one should consider tensor categories themselves over the given tensor. And then this is allowing sort of more generality. Okay, so maybe one thing to say is remarks. So in particular, it's important in this definition that you don't just have a circ, but you have this D of A. So so an analytic ring is more than sort of a homological ring. Also this category. And so you can think of it, well, if you think of A circ as giving a commutative algebra in condensed stabili groups, you can think of D of A as a commutative algebra. So it's a commutative algebra in categories, say PRL, it's a commutative algebra over D of Z. And if you allow more general commutative algebras over D of Z in the category, like commutative algebras in categories, turns out you get a lot more examples that you can evaluate it on. But maybe let me give an example that will sort of illustrate this. So example of analytic rings, well, one is that we could just take well, simplest example would just be to take d of z and say that everything is
And I forgot. The TXC means what? Is it just the
so derived category of condensed ability.
it's not there, because sometimes
Yes.
human sequence.
Yes. So just to say time interval, right, d of z. But another example is the solid. Right, so we've seen where d of, or we can say r solid. So this is a trivial analytic ring structure. We say that everything is complete. But then we can consider the solid analytic structure. So d of z solid. Well, okay, we've just seen that example. Or d of r solid. But we have at least a few more examples that we can generate. So if we have an inclusion of subrings, so if I don't know, so if R is a ring, is any ring, and R plus is a subring of R, then you could consider, we'll write as d of R comma R plus solid. And by definition, this is going to be those objects. So the underlying condensed ring is going to be R again, but we need to say what the category is, and it's going to be those objects in D of R. They don't have to be solid as an R module, but they have to be solid as an R plus module. So which are solid when restricted to D of R plus. So they map to D of R plus, and they need to be solid as objects.
And so this notation R plus players.
Yes.
So this is so the origin of this. Is it a coincidence or is it somehow motivated? Right.
I believe it was motivated by that example. So in particular, in the notion of adic spaces, one has not only a topological ring, but one also has the subring A plus. And in this sort of dictionary, the idea is that the topological ring is going to give you a condensed ring, but the A plus is going to give you the analytic ring on it. And so it is sort of important in Hoover's theory to consider different to allow the A plus. And here that's sort of corresponding to the fact that it's not only the condensed ring, but the analytic ring. Okay, so I guess probably maybe I won't have time today, but I wanted to sort of say some more about some examples of this. Yeah.
Sorry, just to check. So I guess in the second example, C solid and C are the same sequence groups.
Yes.
They're different design.
They're very different as analytics. Yes. Yes, if we fix R, you'll get different analytic ring structures as R plus varies. I mean, so R plus always induces the same as its integral closure in R, but otherwise, like so, I guess maybe I show you the example where R is Z brackets T, and then R, if you could take R to be just Z, or you could take it to be all of Z brackets T, and you'll get a very different grade. And this also kind of fits with the idea that in analytic geometry, you're supposed, like in algebraic geometry, if you have a ring, like if you have a space, and you have a function, you can define what it means for the function to be non-zero. So you can invert the function essentially. But in this kind of in analytic geometry, one also expects that you can impose some inequalities. That you can say a function is at most one. And actually, this sort of works well in this notion of an analytic ring. Because so actually one common construction of an analytic ring is you start with a given analytic ring and then you can impose some conditions. Like so we've already sort of seen that. You started with the trivial analytic ring structure on C, and then you impose some conditions. Like you looked at objects such that Rhom out of something were zero. And so use that to define sort of, we should do some version in this context of defining functions, defining sort of inequalities, defining both side by inequalities. Okay, so I guess I want to state the theorem. So the existence of the analytic ring structure on R solid is actually, it was a sort of a difficult theorem in the original setup, of all condensed subjects. But in the Link setup, it becomes much easier. It becomes much easier to construct the analytic ring because, because you're defining it by this condition based on a compact projected influence effective object. However, it then becomes a theorem to actually compute the solidification. And so let me state the theorem. So the theorem is, so now let's say R is a finitely generated Z alpha. And in this case, one can give a description of of the solidifications. So, well, the basic generating objects of D of R, so of all condensed R modules, are the three objects on finite sets. And the statement is the solidification of R bracket S is the following object. It's the inverse limit of R brackets S sub I if S is the limit of S sub I for S I. So if you can write your finite set S as an inverse limit of finite sets, then R brackets S solid is this inverse limit of R brackets S, where S sub I ranges over, I mean, so these are a bunch of finite sets, and
can you recall what is R brackets S?
so R brackets S is the free object in condensed R modules on R.
So in other words, just S is
Yes.
Just take what are parentheses are that you explain what yes. The question is how to compute.
Yes.
And
This is important, but I will say a little bit more that might clarify this.
yeah, just so SI is fine. So
So it's the inverse limit of a tower of free modules. So at each stage, you get a free module R brackets S sub I, then you take the limit of those free modules. So recall in the Z brackets S solid, we weren't allowed to take the whole inverse limit, but we sort of put a uniform L1 bound, and then took the inverse limit, and then took the union over all L1 bounds. But here there's no L1 bound, you just take the limit of Z, or R brackets. So let me just comment. So one is that abstractly, this is isomorphic to a countable product of copies of R. So if S is a S, so if you have an infinite profinite set, and if you form R brackets S solid, then abstractly it's a countable product of copies of R. And this requires a little bit of an argument because it's an inverse limit of free modules, but somehow it's an inverse limit along a sequential inverse limit of free modules along surjections. And I think if you choose sort of bases appropriately, that turns into a countable. So, okay, so
so I remember that in 2019 by of the center which is something
yes. So, right, so that's right. So it's related to that, but here, in fact, it's only the case for a light reflected substance. So, right, so abstractly, you can think of, so abstractly, this is R value measures on S, i.e. the linear dual of, let's say, continuous functions, on S, all continuous functions on S, so maybe let's say R coefficients with values, and then you take the linear dual of that. And in fact, this is a free R module. This is outwardly generated free R module. So that's actually true for any finite set S by this ruling. But here it's an easier case of a like finite set. Yes. Yes. So remark. So for any profinite set S, not necessarily light, there's a theorem of Newelling. So if you take functions on S, continuous functions or local constant functions on S with Z coefficients, then this is free as an abelian. And this is a little bit subtle because if you think about S as a co-filtered limit of finite sets, then that writes continuous functions on S with Z coefficients as a filtered colimit that dualizes to give you a filtered colimit of the free modules of just all functions on each of those finite sets.
Yeah, so we see that it's flat, for instance.
Yes. Yes.
But it's not yet
So yes, it's a little bit subtle whether like a filtered column of free modules it's some sort of condition that that's true. And in this case, we just need it for a count. So if you have a sequential column of free modules, and the maps admit sections, the maps are direct summands, and the column is free. So that's actually all that's needed here, but there's also the stronger resistance for any profinite set. So this is used essentially in the non-light.
yes, but here the light setting.
In the light setting, it's
I remember the name of nobody because it also very and at that time I was told that set that science. The problem was but now strangely enough with some modern version of self-directed composition. It's not the
okay, so I actually talk probably very soon. Actually, so let me just say a couple of things, and so I was hoping to speak for this thing, that today. But let me connect us to what was erase this. So okay, so the first thing to say is that this theorem requires some work to prove. Right, but so the output is that so output or consequence of the theorem corollary. Sorry, let me say one thing. So there are other results. So in the Archimedean context, like say over the real numbers with these liquid or gaseous structures, There are also theorems proved by Clausen and Schulze that just deride the liquidification or, well, yes, the completion of a pre-profinite set. But in fact, often they will involve sort of both this kind of inverse limit, but with some sort of like uniform bound condition, and then a colimit over all such conditions. So I just want to point out that there are several other results, well, more difficult results that have sort of a similar format in, well, either the lecture notes, well, either in the various sets of lecture notes, and also right in the course. And this is the case where there's no extra condition. You just take an inverse limit over the estimate. So this sometimes the answer is a little bit simpler. But okay, so a corollary is that okay, so the category of solid R modules is compactly generated, has a compact projective generator. Which is this countable product of copies of. So these are the solidifications of so the solidification of R brackets S for any infinite S is going to give you this, and this the theorem is that these are compact projective generators. Yeah, so small complements, right? So this is also something special to the solid theory. In general, you don't have enough compact projectives in solid R modules, in like modules over an arbitrary analytic ring. But in this case, you do, and in fact, it's also true at the derived level. So in fact, the endomorphisms of this object are exactly the ones that you would expect. So they're given by somehow infinite matrices. So in fact, the endomorphisms, but also the derived endomorphisms of this object are, well, that they're just in degree 0 are is the classical ring of somehow expected matrices. So in fact, D of R solid is the classical derived category of this ring of matrices. It's the classical of this ring of matrices. So this gets back to the earlier point that you can describe D of R solid in purely classical terms, in that you look at all sort of infinite matrices and you would expect to act on a countable product of copies of R, and then just take that as an ordinary ring, and then just take modules of it. So again, R is finitely generated. R over C is finitely generated. So there's this sort of description of D of R solid that is sort of free anything condensed one can make. Okay, and okay, so that is the theorem. Anything else I should say before I stop? So okay, so I guess yeah, so I'm not going to be able to explain the proof of this today. This is sort of the basic theorem on. Oh yeah, sorry, I should explain the tensor product. Also, so I should say something about the tensor product. So also, the tensor product sort of behaves the way that you might expect the completed tensor product. So the countable product of copies of R, solid tensor over R, so I'll write that as R solid, so in the derived sense, of a countable product of copies of R is exactly countable product for n cross n of copies. So the solidified tensor product behaves in the way that anyway, so it's past 6:30. So maybe I should just say, I guess maybe in the future I can explain the proof of this result and then give some examples, for instance. But probably I should stop for today.
After all, the notion of solids are modern. Yep. We also have liquids, which, for instance, a liquid theory, which is modern version of classical functional analysis, which actually I'm trying to guess, but this is what I'm trying. So the naive idea would be that instead of so infinite product is so to say all sequence, all sequence. Instead, one would try to axiomatise of sequences proof condition instead of style. But now there are so this something can the liquid theory here formulated in this manner. So
So, right, yes, I mean, abstractly, yes. So, okay, so one is, you should say that the liquid theory, so as an abstract, the liquid theory was set up in, well, in an earlier set of lecture notes that was not using the light setting. And so one thing that means is they can't, that this sort of, these kinds of manipulations with null sequences don't quite give you analytic wings. I mean, so they have to, they define the liquid theory by essentially by writing down what this is supposed to be. So by writing down what the completion is supposed to be, but then it takes a lot of hard work to show that that's actually a localization factor. But so, right, so they define the liquid theory essentially by doing something like this, but where, say over the real numbers, and you look at R brackets S sub I with some, I guess some LP norm condition.
when you say over the real numbers, you cannot consider there are real numbers of built conditions, or in principle you could consider integers like this. So,
I think they, so, okay, so, right, so I guess one thing to say is that I think they actually do approach the real theory by thinking of power series in Q over Z. And that's also as far as what they're doing in the more recent lecture series. So in the more recent lecture series, they consider like they consider power series. They consider this ring Z brackets Q hat that has come up, and then they define the completion of it such that the object that you get looks like power series in Z power series in Q, but where there's a growth condition on the coefficients. It's a polynomial. The coefficients have polynomial growth. So that's what they define, and they define it, as I understand it, in a somewhat similar way, like by imposing a condition on null sequences. So in the liquid, at least in the liquid theory by construction, it's in the non-light condensed setting, so you have compact projector generators. So in principle, you can define it purely algebraically because as a functor from some additive category into Abelian groups, the compact projective generators. Then it's not, I guess it's not clear in these settings here whether the category you get will be of that form, will have compact projective generators. So I think the answer is in principle, it should be possible to sort of say roughly what a liquid vector space is in terms of sort of more, sort of maybe not entirely classical, but somewhat, well, in terms of relatively concrete objects, like topological bar vector spaces. The caveat is that maybe that they have to work with some sort of funny convexity conditions on that, as far as I understand. But it is a category with compact projective generators, so in principle you can describe it sort of.
And what about plural conditions? So, so maybe I'm thinking about when people think about sequence version 0 and then well, and then giving the analysis of the form. Some, in order for the sum merge, it's not enough to